In the last video, we started to talk about the geometric interpretation of uniqueness. Specifically, we talked about the fact that solutions cannot intersect. Because if solutions intersected, then we could choose the intersection point as the initial point. And if existence and uniqueness holds, the solutions would necessarily have to be equal. So as long as the existence and uniqueness theorem holds, then we can say that solutions cannot intersect. Well, there are going to be some consequences of the fact that solutions cannot intersect. Okay, and there's going to be consequences of the fact that we might have existence and uniqueness. Okay, so I want to show that y of t equals 1 is the solution to dy dt equals y squared minus 1 e to the cosine of t y, and the initial condition y of 1 equals 1. So the first thing that I have to do to show that this is the solution is first I need to show that it is a solution. So I need to take the derivative, and the derivative of 1 is, of course, 0. And then I need to look at the right-hand side. Specifically, I need to see if what y squared minus 1 e to the cosine of ty is. So I'm going to substitute in y equals 1, and I'm going to get 1 squared minus 1 e to the cosine of 1, which is, of course, 0. And so y of t equals 1 does satisfy the differential equation. And in fact, it satisfies the initial condition. Y of 1 is equal to 1. So I can say that y of t equals 1 is a solution. In fact, it's an equilibrium solution because that is where the derivative is 0. But now I want to say it is the solution. And the way that we can do that is show that the differential equation satisfies the existence and uniqueness theorem. So the right-hand side, f of ty, we said is y squared minus 1 e to the cosine of t times y. And we have a polynomial, y squared minus 1. We have an exponential, and we have cosine of ty, and all of those things are continuous functions, and we're not dividing by 0 anywhere. So we can say that this is a continuous function. Okay, it's actually continuous everywhere. Now we need to take the derivative of the right-hand side with respect to y. So using the product rule, I get 2y times e to the cosine of ty. And then I'm going to add y squared minus 1 times the derivative of e to the cosine of ty, which is itself, times the derivative of cosine of ty, which is negative sine of ty, times the derivative of ty, which is t. And that is, although complicated, just polynomials, exponentials, cosines, and sines, and so that is also continuous. Okay, so therefore, our solution must be unique. So we can say that the solution that we found, y of t equals 1, is not only a solution, it is the solution. So that's a consequence of uniqueness. I was able to show that y of t equals 1 is the solution. Now, another consequence of uniqueness is that since solutions cannot intersect, we can say each solution actually is going to divide the plane into regions. And those regions are going to constrain where other solutions may exist. This is best going to be demonstrated with an example. Okay, so we're going to actually look at the same differential equation. Okay, dy dt equals y squared minus 1 e to the cosine of ty. And we already found that y of t equals 1 is a solution. So that actually divides the plane into two regions. Okay, and we can say that solutions that start above 1 are actually going to remain above 1 because these solutions cannot intersect. So if I start a solution above y equals 1, then it must remain above y equals 1. So if we found some more solutions, we could further divide the plane into regions. So dy dt equals y squared minus 1 e to the cosine of ty. I'd like to find some other solutions, so why not look for equilibrium solutions? So I'm going to set this equal to 0. Now the exponential can't be 0, so that means that y squared minus 1 would have to be 0 to get an equilibrium solution. And so I have two equilibrium solutions, y equals 1, which we already knew was a solution, but also y equals minus 1. And so that further divides the plane up into regions where solutions cannot cross. Okay, so that means if I start below minus 1, the solution will approach minus 1, as you can see from the slope field, but it'll never actually touch minus 1. Okay, so solutions that start below minus 1 will remain below minus 1 because the solutions cannot cross. Okay, so specifically, we could be then interested in what happens when y of 1 is 0. What happens if I start between minus 1 and 1? So I'm going to let y of 1 be 0. Well, if I'm following the slope field, you can see solutions start to decrease from minus 1 or from 1, and then they continue to decrease to minus 1. But again, the solutions don't cross. So if I start at a point that's in between minus 1 and 1, it should remain between minus 1 and 1. So let's kind of summarize that. So since y equals minus 1 and y equals 1 are solutions, and solutions cannot intersect, if I start at an initial value between minus 1 and 1, say y of 1 equals 0, then y remains between minus 1 and 1. And this is important because I can say something about the solution to the differential equation without having to know what the solution formula actually is. I'm not going to be able to solve this differential equation. It's too complicated. It's not linear. It's not separable. I'm not going to be able to find an explicit formula for the solution, but I can say something about solutions anyway. If they start between minus 1 and 1, they will remain between minus 1 and 1. If they start above 1, the solution, then it'll remain above 1. And if they start below minus 1, they will remain minus 1. In fact, I can add a bunch of solutions on a slope field like this, and you'll see starting above minus 1, or sorry, starting above 1, they remain above 1. Okay, in between minus 1 and 1, they remain between minus 1 and 1. And starting below minus 1, they remain below minus 1. Now, you might say, as you're looking at this picture, oh, the solutions are intersecting. Don't you see that the lines are intersecting? And that's actually not the case. What the case is that the solutions are actually getting infinitely closer to, say, minus 1. And what's happening is you're seeing the thickness of the lines actually intersect, okay? So it's only the thickness because we're trying to display the solutions here that are intersecting. The solutions themselves are not intersecting. Okay, let's move on to one more example. Let's go back to Torricelli's law, which we talked about in the last lecture. We were draining water from a bucket, okay? And the differential equation that describes that is that dy dt is equal to -2 square root of y. And we'll start with an initial condition that y of 0 equals 4. Now you can solve this using separation of variables. And so I am suggesting that you pause the video and that you solve this equation using separation of variables and then try to answer a few of the questions that are below. And then we'll get back together and we'll talk about it. So take a second, pause the video, and solve the differential equation. I'm assuming that you've now solved that differential equation, so we're going to go ahead and do it together just for practice. dy over square root of y, if we're going to do separation of variables, would equal minus, I would do minus 2 dt, but let's go ahead and divide by 2 anyway. That's going to help us find that antiderivative, because it turns out the derivative of square root of y is actually 1 over 2 square root of y. Okay, so square root of y is equal to, in this case, negative t plus c, anti-differentiating both sides. Let's find out what c is. Y of 0 happens to be 4. So that tells me that the square root of 4 must equal 0 plus c. So that tells me that c must be 2. So the square root of y in this case is equal to negative t plus 2. So y in this case must be negative t plus 2 squared. Okay, the solution is a parabola. And I've actually graphed the parabola on the screen for you, as you can see. And I graphed the physical part where you can see the height of the water draining from the bucket. And then I also graphed with the dotted line kind of the non-physical part of the solution. That was a strange occurrence that happened when we were solving this differential equation, where we thought, oh, spontaneously the water is filling back up in the bucket, which didn't make sense. And now I'm going to kind of make sense of it, thinking about existence and uniqueness. Okay, so I found my solution to the differential equation, but wait a minute, is y equals 0 also a solution? What happens if you take the derivative of 0? Well, you would get 0, but negative 2 squared of y in that case is also 0. So y equals 0 is also a solution. And I've actually graphed that on this plot as well. Okay, so I've made a little dotted line here that graphs y equals 0 as it goes across. And you'll notice something, that these two solutions actually intersect. They intersect when t equals 2. Okay, the parabola at t equals 2 touches that t-axis. And so the two solutions intersect. So did I violate the existence and uniqueness theorem? Because now I've got two intersecting solutions. Well, the answer to this is no, I have not actually violated the theorem. Why is that? Well, we have that f of ty, the right-hand side, which is negative 2 square root of y, that is continuous when y is bigger than or equal to 0 at least. And that's where our solutions exist. Okay, but the derivative of f with respect to y is actually negative 1 over the square root of y, and that is not continuous at y equals 0. And notice that's exactly where our intersection occurs, right here at y equals 0. And so we have two solutions that intersect at y equals 0, right? And so we are not guaranteed uniqueness at y equals 0. Now notice it doesn't mean that you don't sometimes have uniqueness when y equals 0, because sometimes you do have a unique solution, right? But at t equals 2, we had that intersection. So we're not guaranteed uniqueness at y equals 0. And so we have not violated the theorem because we didn't satisfy the conditions of the theorem. The derivative was not continuous at y equals 0. In fact, I like to think about the physical solution to this problem as being a combination of these two different solutions. We have that parabola, y equals negative t plus 2 squared. that describes the water as it's draining from the tank. It's the height of the water as it's draining from the tank. But at t equals 2, that tank, that cylindrical tank is empty. And then the solution y equals 0 takes over, okay, because there's no longer any water in the tank, and there will not be any water in the tank for all time after time t equals 2. And so really the part of the parabola before t equals 2 and then y equals 0 after t equals 2 form the true physical solution here.